everyone, and thanks for watching Edupedia World Videos. In this video we'll study a new topic called fluid dynamics. So the definition of fluids, the scientific definition of fluids is fluids are the superset of liquids and gases. So basically anything that flows, liquids flow and gases flow, so they are both considered fluids. So technically whatever we learn in this chapter should be equally valid for liquids and gases. And we'll take some assumptions which will make our calculations easier. The first assumptions we'll take is that all fluids we'll study will be incompressible. Incompressible means their volume does not change with pressure. So, though technically what we study should have been valid for liquids and gases, gases we know are not incompressible. If you increase the pressure on a gas, the volume will change. It does happen with liquids as well, but to a very small extent. If you put some water in a glass and you push it from above in such a way that no water escapes, the volume will decrease slightly, but it will mostly not be noticeable. So for liquids, we can pretty much assume this to be true. The second quality which we will assume our fluids to have will be that they are non-viscous. So before knowing what non-viscous means, we need to know what viscosity means. Viscosity is the analog of friction in fluids. Whenever two solid objects rub against each other, the force of drag is called friction. Whenever a solid rubs against a liquid, or whenever two liquids rub against each other, the same force of drag is renamed viscosity. And when we assume fluids to be non-viscous, that means there is no frictional force within them. That means I could take a small object, let's say a ball, and I could move that ball through some liquid and there would be no force of drag. There would be no force decreasing the velocity. Now that is not true. We know that if we throw an object in water, it will eventually decrease its velocity and come to rest. But we will assume that not to be true. We will assume that all our liquids are completely non-viscous. So let's start. Whenever we talk about a fluid in a container, the most important quantity is pressure. Just like force is the most important quantity in Newton's laws of motion, when we study fluid dynamics, pressure is the most important quantity. So the first thing we need to do is define pressure. So we can take any small point, let's call that point P, and we can make a small area around that point. Let's call that area delta S. Delta S is a very small area, remember. So the first thing we need to know is that any area, any time, and this is not a real area, this is not a real object, we are just imaginarily, we are dividing these two liquids into two parts separated by this small area. So anytime we have this small area, these two sides will push each other with a force. So the definition of pressure is limit delta S goes to 0, that particular magnitude of force by delta S. So this seems like the familiar definition which we have, which is pressure is force by area, except force is the magnitude. So from that we see that first of all pressure is a scalar. Secondly, the orientation of delta S does not matter. If instead of taking it slightly tilted like this, if I took delta S to be this, then both sides, as long as delta S was the same, would have pushed each other with the same force. I could have taken the area to be like this, and as long as in this figure it looks as though delta S is bigger, but if delta S was the same size, the force would have been the same. So in incompressible non-viscous liquids, the force applied by any small imaginary, by two parts of the liquid on each other when they are separated by any small imaginary area is independent of the orientation of delta S, and hence we can talk about the pressure at a point. So So for incompressible non-viscous liquids, pressure at a point has some significant meaning. It means that at that particular point, if you make any small area, the orientation is irrelevant. Both sides of fluid, opposite sides of that area, they would push each other with a force F such that the pressure, which is F by delta S, would be independent of the orientation. Right. So this is the most important point which beginners sometimes have confusion with. So the most important thing to remember here is that the orientation does not matter, and that is the only reason we can talk about pressure at a point. Next, let's talk about the difference between pressure at 2 points. So let's say we have some liquid and we take 2 points, P1 and P2. Right. And we want to find the pressure difference between these 2 points. So what I can do is I can make some cylindrical volume and I can consider these two surfaces. If I consider this particular mass of water and I draw the free body diagram of that mass, it will be like this. Since pressure is always pushing at the two sides, there will be a pressure at point P1 pointing downwards. So there will be a force P1 delta S, where delta S is the perpendicular area, that is the area of the horizontal circle, P1 delta S. Similarly, upwards there will be a force P2 delta S, where P2 is the pressure at this point. So P2 into delta S will be the force that is applied upwards. Also, there will obviously be a force of gravity acting, mg, and there is no other force acting on this liquid. So we know that since this particular part of the liquid is in equilibrium, it is not moving anywhere, these three have to be equal. What that means is P1 delta S plus mg is equal to P2 delta S. Mg can be written another way. Mg can be rho, which is the density, times g times the volume. If this height is h, the volume can be written as h delta S. So we see delta S cancels from these equations and we get the most important result in fluid dynamics. P2 is equal to P1 plus rho gh. The pressure at the bottom is greater than the pressure at the top by an amount rho gh, where rho is the density of the liquid, g is the acceleration due to gravity, and h is the height between the 2 points. So a lower point will always have a pressure greater than the higher point, and that's understandable because at the higher point the mass acting on that is this much, but at the lower point we have a greater mass acting on it in terms of the gravitational force. So this is the most important result, and everything else which we derive will ultimately come from this result. The first important law which we need to study is Pascal's law. And Pascal's law can be derived from this particular equation, P2 is equal to P1 plus rho gh, but it actually was stated by Pascal before this law was derived. It states that if pressure in a liquid is changed at a particular point, then the change is transmitted to the entire liquid. Without diminishing in magnitude. And here's what that means. Let's say we have some fluid within a container, and this point has some pressure P1, this point has some pressure P2. There will obviously be some atmospheric pressure, let's call it P atmosphere. We know that it is generally equal to 1.01325 into 10 to the power 5 pascals, or 1 atmosphere, but that's not relevant here. So there will be an atmospheric pressure acting here. So that pressure will be the pressure at this point. We know that pressure at this point will be rho gh higher than the pressure at this point, where h is this height. Similarly, the pressure at this point will be rho gh higher than the pressure at this point, where now h will be the height between these 2 points. So the moment we decide the pressure at one point, we know that pressure at every other point on the liquid, which will simply be rho gh plus the pressure at this point, where h will be the distance of that point from this point. Now let's say, along with P atmosphere, we apply more pressure. We apply, let's say, 5 atmosphere more of pressure. That is nearly 5 into 10 to the power 5 pascals of pressure. By the way, pascals is the SI unit of pressure, Newton per meter square. So then, at this point, the pressure initially was 1 atmosphere, now it's 6 atmosphere. So the pressure is increased by 5 atmosphere at this point. Now whatever happens, because this liquid is in rest, the pressure at this point has to be, let's say this is 1 meter and this is 3 meter. The pressure at this point has to be rho into g into 1 more than the pressure at this point. The pressure at this point has to be rho into g into 3 more than the pressure at this point, or rho into g into 4 more than the pressure at this point. Meaning the difference between these two pressures will always be rho gh. So if I increase the pressure by 5 atmosphere at the top, every point in the liquid will have their pressure increased by 5 atmosphere as well. And that statement is derived from the fact that if we take this particular cylindrical liquid to be in equilibrium, the difference between pressure at these 2 points has to be rho gh. So if the pressure at the top is increased by a certain amount, the pressure at the bottom has to also be increased by a certain amount. We see another result here, which is that at the same horizontal level, the pressure is the same. We saw that the pressure between 2 points, P2 minus P1 is equal to rho gh. If h is 0, that means P1 is equal to P2. So at the same horizontal level, the pressure will be the same. We'll see an exception to this rule later, but right now remember we are deriving these rules for the liquid to be at rest or in equilibrium. If the liquid is accelerating, then P2 minus P1 will not always be rho gh, and then the two horizontal points will not necessarily have the same pressure. But if the liquid is at rest, then P2 minus P1 will always be rho gh, and if h is 0, P2 will always be equal to P1. Let's look at the first major application, which is the barometer. Barometer is a device which is used to measure atmospheric pressure. So we can measure the pressure exerted by the air at any point due to the barometer, by the barometer. So this is the way it works. You could technically do it with any liquid, but for reasons of practicality, we do it with mercury instead of water. So we have some mercury in a bath, and we have a tube which has some mercury as well. So what we do is, first of all, we take the tube upright and we put some mercury in it, right? We fill it with mercury till the top, and then we close off the top, and then we invert it and then put it in here, so that theoretically this should be completely filled with mercury. Except when we do that, we find out that this mercury, if the length of the tube is big enough, this mercury level falls a little bit shorter, and there's really no mercury in some topmost portion. The mercury stops here, it goes down and it enters into this bottom pool of mercury, and there's a vacuum in this place. Vacuum because initially we covered the tube with mercury, we tilted it, and then we inverted it and put it in here, so there was no way for any air to escape inside this point, right? Now we look at the pressure at this point P1 and the pressure at this point P2. Since the whole liquid is in equilibrium, the pressure at these 2 points has to be the same. We just derived the result that pressure at the same horizontal level is the same. So we know that P1 is equal to P2. But what is P1? P1 will simply be the atmospheric pressure. If we were talking about this point, it would be the atmospheric pressure plus rho gh, where h was this side. But since this is at the surface of the liquid, the surface will always have a pressure of P atmosphere. That is equal to, now P2 will have the pressure equal to the pressure at this point plus rho gh. We know the pressure at this point is 0 because there is a vacuum above it. There is no air to exert any pressure. So if this height is h, this should be equal to rho gh. And thus, I have an instrument which helps me measure the atmospheric pressure. Right. So now when you do it with mercury, you find out h is equal to 76 centimeters. That means we say that the atmospheric pressure is equal to 76 centimeters of mercury. If you were, because mercury is much more dense than water, if you were to do it with water, rho would be much smaller, so h would need to have been much higher, and we would need to have a much bigger tube. And that is the reason for practicality why we choose mercury over water, because mercury is much denser than water. Another thing, what would happen if the length of the tube was smaller than h? So if this is the liquid, then there would be no vacuum, there would be liquid till the top, and if this h is smaller than 76 centimeter, then the top of the tube will exert the remaining pressure on the liquid. So we will have atmospheric pressure is equal to rho gh plus the pressure exerted by the top of the tube, the glass, on the liquid. And if we have a tube of sufficient length, then the liquid will drop down, there will be a vacuum created, and the pressure will be equal to the height of the liquid. So when you hear a term, the pressure is equal to 76 centimeters of mercury, that just means the pressure is equal to rho gh, where rho has to be taken as the rho of mercury. The rho of mercury is 13,600 kilogram per meter cube, whereas we know for water it's 1,000 kilogram per meter cube. So if we were doing it with water, we would need the length of the tube to be 13.6 meters as opposed to 1 meter, which we generally take to be. So this is an instrument with which we are able to measure the pressure. A lot of questions you'll see will be involving something called a faulty barometer. So I'll just explain how this works now. To be able to actually calculate it, we would need to have studied specific heat capacities of gases and kinetic theory of gases, which we will later. So in a faulty barometer, all that happens is, when we have the tube filled with mercury and we cover it at the top and we invert it, we did not do that process precisely, and in the end, along with this mercury, this part has a little bit of air, not vacuum. And if there is some air in this part, then the pressure of the atmosphere will not simply be rho gh, but rho gh plus the pressure of this air. So, and then in the question some things might be given so that we can calculate this pressure of air, or for example they might say that if we take a different material, then this is the amount, and with those two things you'll be able to calculate the height and the air, and so on. You can do that later on once you calculate the relationship between volume and pressure for air, which we'll do in kinetic theory of gases. Right now all you need to know is the meaning of a faulty barometer is that this is not vacuum at the top, there is some air, and P atmosphere will in this case be rho gh, where this height is h, plus P air, which will usually be a small amount, but it might be there. So this completes our study of the barometer. The next important instrument is similar to the barometer. It is called the manometer. And just like the barometer measures the atmospheric pressure, manometer measures the pressure of a gas in a box. So this is the way it works. So let's say we have a box full of some gas which has a pressure P inside it. To this we can connect a manometer, that is, let's assume there is a small hole at one point through which gas can escape. So the manometer looks something like this. And it is nothing but just a tube which has some mercury. And in ideal case, if you keep it flat like this is atmospheric pressure, this is atmospheric pressure, so both the sides would have the same level of mercury. But if there is some liquid applying a pressure, you can just see that if you blow through this side the liquid level would drop, and in this side it would rise. So when there is some pressure, this is how the mercury in the manometer looks like. Let's say this height is h. H is the difference between the levels of liquids in the two arms. It is not just level of each of them. It is not from the ground. It is from this point. The difference is level of liquids between the two arms. So at this point the pressure will be P, because there is no atmosphere connected, there will be no P atmosphere. That will be equal to rho g h. We want the pressure at this point. These two will be equal. That will be rho g h plus the atmospheric pressure. Because this end is now open to the atmosphere would also apply a unit of 1 atmospheric. So this will be the pressure inside the gas. By the way, this term rho gh, the height difference between the two arms multiplied by rho multiplied by g has a special term. It is called the cage pressure. And the total pressure is this plus the atmospheric pressure. This is the term which students sometimes forget.